In this lesson, we will explore limits involving infinity. This may mean limits where we are approaching infinity as we approach a certain point from above or below, or it may mean that we are looking at what happens as x approaches infinity, and we'll look at both of those cases. Okay, so limits involving infinity. So we may have a limit. So if we have the limit as x approaches 0 from below of 1 over x, or the limit as x approaches 0 plus of 1 over x. So we're going to look at the single-sided limit, the left-hand and the right-hand limit, for the function y equals 1 over x. So let's start by looking at this in an intuitive graphical way, as we started with regular limits. So our graph of y equals 1 over x looks like this. And we can see that we have a vertical asymptote at x equals 0. Okay? So we have this vertical asymptote here. So what we want to do is we want to be able to describe what the graph is doing. So the way that your book uses this terminology, and there are places where it is used differently, is that we would say, as we look, as we're approaching 0 from the left, so 0 minus, we are going to be coming and we're going down to 0. So y values are getting smaller and smaller and smaller and smaller and smaller. So we would say the limit as x approaches 0 from below of 1 over x is equal to negative infinity. Now, we haven't yet looked at a formal definition of limits, and this is not correct as written. If we think of the equals as an equal sign and we think of negative infinity as a number. This is a bit problematic because we can't treat this as being equal. This doesn't mean the limit is negative infinity, because negative infinity is not a number, so nothing can actually be equal to it. What this does is this is a description of what happens to the y values. So what this description is telling us here when we say the limit as x approaches 0 from below of 1 over x equals negative infinity, we are saying that the y values continue to decrease. The y values are approaching negative infinity. They will never get there. It is not a number, but they will, as we approach 0 from below, they will continue to get smaller and smaller and smaller and smaller. That is what that means. Similarly, as we approach 0 from the positive side, okay, so we're approaching 0 plus, we are going up, 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 and the y values are continuing to get bigger and bigger and bigger. So we're going to say that this equals positive infinity, but again, this doesn't mean that the limit is equal to positive infinity. So this right here says y values continue to increase. The closer and closer we get to 0, the more and more they increase. Again, it's a descriptor. It's not actually, we are not saying it is equal to the number, but it is useful because it tells us something about what's happening with the graph. So here, this says the limit, when we have an asymptote, we know that we can either our y values can either go down infinitely or they can go up infinitely as we approach an asymptote. So taking the limit on both sides here allows us to see what's happening on either side as we approach the asymptote. So this one says as we approach from the left, we're going down as we're heading towards the asymptote, and as we approach from the right, we're going up. Okay, so this is one way to think about it, okay? We can also think, so the second way to think about it is we can think about what's happening as x approaches infinity. What is what we call the end behavior, what's happening out there, Okay, so let's take a look at another one. So the limit as x approaches positive infinity of 3x. So as x gets bigger and bigger, what's happening to our y values? Well, we have a straight line, 3x, it's going up. So our y values will also continue to get bigger and bigger. So we have limit as x approaches infinity of 3x equals infinity, which means the y values are continuing to increase. Similarly, we have the limit as x approaches negative infinity of 3x equals negative infinity. So what that means is as x's get smaller and smaller and smaller, the y values also just continue to get smaller and smaller and smaller. And we have to remember, again, similarly here, this does not actually equal that. X never gets to infinity, y never gets to infinity. But these are what they are approaching, okay? These are what the y values approach, or where they are heading to, okay? So when we are looking at polynomials or rational functions, generally we are the most concerned with, so let's take a look at polynomials, okay? So polynomials and constants. So with a polynomial, we really only care what the highest degree term is doing. So let's take, because what happens is as we get bigger and bigger and bigger, x squared is going to start increasing so much faster than, say, minus 7x, that minus 7x, the bigger and bigger and bigger x gets, that minus 7x is almost going to be like nothing anymore as we get bigger, really, 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 really big. Think a million squared minus 7 million. A million squared is going to be so much bigger that minus 7 million won't even make a difference. So let's have a look. So we have the limit as x approaches minus infinity of x squared plus 3x minus 6. We're only going to care about only look at the highest degree term. So with a polynomial here, we're only going to care about the x squared. So this is going to like a negative infinity squared. And then that goes to positive infinity. So the limit here is equal to positive infinity because we're squaring our negative infinity, and that's the term that's going to count as we get bigger and bigger and bigger and bigger. Okay? So let's say we had a different one. If it was the limit as x approaches negative infinity of negative x squared plus 3x minus 6, then this would be negative infinity squared. We always substitute in here. And notice I'm using arrows here and not equal signs just because we're really not fully equal. We're just saying that this is going to be now a negative infinity. So the limit over here is equal to negative infinity. Okay, again, equal negative infinity. It means as x approaches negative infinity, as x gets smaller and smaller and smaller, y values also continue to get smaller. Okay, well, what if it's a constant? So what if we have the limit as x approaches infinity of pi? Well, we have a flat line. As we get bigger and bigger, it still is a flat line. So that is still equal to pi. Okay, so what happens if we have rational functions? Okay, so if we're looking at the limit as x approaches infinity, we want to divide every term by the highest degree of x in the denominator. Of x in the denominator. Okay, so let's look at an example. We have the limit as x approaches infinity of 7x cubed plus 6x squared over 5x squared plus 2. Okay, so now what we're going to do is we are going to divide everything by x squared. Divide each term by x squared. So this is equal to the limit as x approaches positive infinity. Notice we don't have to worry about x being 0 here because we're approaching positive infinity. As we get bigger and bigger and bigger, we're not 0. We're not being 0 at the same time. We're also getting bigger and bigger and bigger. So we don't need to worry about that situation here. So this is 7x cubed over x squared plus 6x squared over x squared over 5x squared over x squared plus 2 over x squared. So we can here cancel everything that we have here. Sorry, not 2x squared. That should be 2 over x squared. As we approach positive infinity, anything that has a power of x that's not equal to 0 in the denominator is going to approach 0. Okay, so this is going to be equal to 7 times the x cubed cancels with the x squared. 7 times positive infinity plus 6 divided by 5. Well, a number times infinity plus 6 divided by 5 is still just positive infinity. So that means that that function will continue increasing. There are no horizontal asymptotes. Example 2. Okay, the limit as x approaches negative infinity of 8x to the 4th plus 2 over 2x squared plus 6x minus 1. We're going to divide the highest power of x in the denominator is x squared, so we're going to divide everything by x squared. So this is equal to the limit as x approaches minus infinity of 8x squared plus 2 over x squared over 2 plus 6 over x minus 1 over x squared. So we're dividing everything by x squared. So anything that has an x in the denominator is going to go to 0 as we go to infinity. Anything over a big number, so that will go to 0. So we end up with this being equal to 8 times negative infinity squared over 2, which gives us positive infinity. So this function is going to keep increasing as x gets smaller and smaller and smaller. So as x goes to negative infinity, gets smaller, y values are going to increase, get bigger. Okay, let's look at another one that does something slightly different. And some of you may start to link this to what you learned in Pre-Calculus 12 about horizontal asymptotes and how they behave based on the powers of x that are in the numerator and the denominator. So think about that and see about recalling what happens if you have a higher power of x in the numerator. What happens if the higher power is in the denominator? What if the powers are the same in the numerator and the denominator? So example 3, the last two examples we looked at were where the power of x in the numerator was higher. So we have the limit as x approaches negative infinity. So we have 6x squared plus x minus 2 over 4x cubed minus 6. So here the higher power of x is in the denominator. We're going to divide everything by x cubed because that is the highest power of x in the denominator. So we have 6 over x plus x divided by x cubed is 1 over x squared minus 2 over x cubed all over 4 minus 6 over x cubed. So what we have is everything with an x in the denominator goes to 0. So that means our whole numerator is going to 0. And our denominator, that piece is going to 0. So we end up with 0 over 4. So this is just equal to 0. because we have a numerator that is equal to 0. And that, as you can see, will always happen when the highest power in the denominator is higher than any of the powers in the numerator. Let's look at an example where they're the same, just to see what happens there. So the limit as x approaches negative infinity of 3x squared plus x over 6x squared minus 1. Okay, so as we are approaching negative infinity, what we find, we're going to divide everything by an x squared. So we have the limit as x approaches minus infinity of 3 plus 1 over x over 6 minus 1 over x squared. So these bits both go to 0. Here, the 3 over 6 is going to stay. So this is equal to 3 over 6, which is equal to 1/2. So that gives us a horizontal asymptote that's equal to the coefficients divided by each other. Okay, well, let's look at it. Can we get something that's a little bit more interesting? Is it possible? So with all of these ones that have had asymptotes, so examples 1 and 2 didn't have asymptotes. Examples 3 and 4 did. Is it possible? And you see, we did positive infinity for one, negative infinity. We did negative infinity for both. But as you can see, we're really just looking at things going to 0. So even if we had used positive infinity, we would have wound up with the same asymptote. Is it possible to have a function that has horizontal asymptotes that are different on either side? Well, the answer is yes, and this gives us probably our most interesting example for this lesson. This is fun. I think it's really fun, and it is probably likely to show up on a test. So find the horizontal asymptotes for f of x equal radical 3x squared plus 2x minus 1 all over 6x plus 7. Okay, so when we are asked to find the horizontal asymptotes, what we are being asked to do, interpreted in the context of limits, is find the limit as x approaches positive and negative infinity. Okay, so we actually have to do both of these. We find the limit as x approaches infinity, and we find the limit as x approaches minus infinity. Okay, we're going to do both. So let's look at plus infinity. Okay, so the limit as x approaches infinity of radical 3x squared plus 2x minus 1 over 6x plus 7. Okay, so we're going to divide everything by the highest power of x in the denominator, which is x. In order to divide under the square root, I'm going to be multiplying. So think about, I'm multiplying everything by 1 over x, but 1 over x is the same as 1 over radical x squared when x is positive, right? So 1 over x is the same as 1 over radical x squared when x is positive, because this is always going to come out positive, okay? This is greater than 0 always, greater than, okay? So we know that x isn't 0. Again, we don't need to worry about x being 0 because we're approaching infinity. We're getting really, really big. We're not anywhere near 0. So I'm going to multiply the numerator by 1 over radical x squared. And the reason I'm doing that is because I want to get it. So I'm going to actually make this, instead of 1 over radical x squared, I'm going to make this radical 1 over x squared, because that is the same thing. And multiplying a radical times a radical, gets me inside that radical. This I'm going to multiply by 1 over x. It is okay to do this because these are the same because of that. So once I've done this, this is the same as the limit as x approaches infinity of radical 3 plus 2 over x minus 1 over x squared. Radical of something that goes to 0 is still going to be going to 0. In the denominator, we get 6 plus 7 over x. This is also going to head to 0. So this limit is equal to radical 3 over 6. Okay. So now we have to look at the limit as x approaches negative infinity. Every other case so far, it should be the same, but in this case, it's not going to be. And the reason is, so we're going to take the limit 3x squared plus 2x minus 1 over 6x plus 7. So let's consider what happens when 1 over x is negative. So if this is negative, and we consider 1 over radical x squared, this is always positive. So in order to make this equal, the number, the absolute value of these are going to be the same. This has to be negative. So we have to make that negative in order to make these equal when x is negative. And it can be hard. Sometimes retraining your brain to say, you see an x a lot of times, and x looks positive to you because it's just a variable. So just a variable, you just kind of assume it's positive because positive numbers are more natural to think in. You have to remember that anytime you see a variable, it could be positive, it could be negative. We don't know for sure. So we're going to now go and multiply everything by negative radical x 1 over x squared, and that negative can't go under the square root because it's an even root, so that negative is going to have to get pulled out front. So this is the same as the limit as x approaches minus infinity of negative radical 3 plus 2 over x minus 1 over x squared. I'm going to multiply this by negative radical 1 over x squared over 1 over x. And the reason we can do these is because these are the same. We said 1 over x is equal to negative radical 1 over x squared. So now we've got this. We are dividing by x on the bottom, so that's 6 plus 7 over x. Everything that heads to 0 heads to 0. And we're left with negative radical 3 over 6. And you guys can go ahead and graph this in Desmos and just check out what it does. There will be 2 different asymptotes for this graph. So our horizontal asymptotes are y equals radical 3 over x as x goes to positive infinity, and y equals negative radical 3 over x as x goes to negative infinity. So those are the values of our horizontal asymptote lines, the ones that we are approaching but never going to get to. Okay, a couple more examples. So we've looked at what happens at the very beginning. We looked at a case that involved vertical asymptotes. So limits involving infinity are almost always going to involve asymptotes, or they will just involve functions getting bigger and not having an asymptote. So we've looked at a bunch of ways of looking. So functions where x is approaching positive or negative infinity, we're looking at horizontal asymptotes. Functions where x is not approaching infinity, but is where you're going to get a result that y values are approaching positive or negative infinity, are going to involve vertical asymptotes. So let's look at some cases involving vertical asymptotes, because these are also limits that involve infinity. Okay, so let's look at the limit as x approaches 1 from below of minus 2 over x minus 1. Okay, this is equal to, as we're approaching positive 1 from below, we have negative 2 in the numerator, and we're going to have a 0 in the denominator. So when we were looking at these limits, we said, well, when it's above 0, it doesn't exist. We want a little more information, though. We're coming at 1 from below. We want to know, we know it's not going to exist at 1, but we want to know, is it going up? Is it heading for positive infinity? Or is it going down? Is it heading for negative infinity? So here, we look at, if we have something that's just a little bit less than 1, minus 1. So something a little bit smaller than 1 minus 1. As we get closer and closer to 1, we're going to be getting closer and closer to 0, but we're going to be doing it from below. So the way we would write that is that we would write this as a 0 minus, which means just below 0. So as it's getting close to 0, it could be doing it from above or from below, but if it's doing it from below, that means it's going to be negative, and if it's doing it from above, that means it's going to be a very, very small positive number. So here we have a negative divided by a negative, which is going to give us a positive infinity. So that means as we approach 1, we're going to have a vertical asymptote at 1. As we approach 1 from below, we're going to see positive infinity. We'll look at the graph in a minute. So let's see the limit as we approach 1 from above of negative 2 over x minus 1. So this, again, if we're taking something a little tiny bit bigger than 1 and subtracting 1, we're going to end up with 0, but with something that's just a little bit bigger than 0, that's not equal 0, but it's getting closer and closer, but from that positive side. So that is going to give us a negative infinity because we have a negative divided by a very, very small positive. So we're going to be getting, as we get closer and closer to 0 from above, we're going to be getting smaller and smaller and smaller and smaller. Okay? So our limit, as we had discussed before, we have a limit that's going to positive infinity. We have a limit that's going to negative infinity. So we can't say that the limit as x approaches 1 of negative 2 over x minus 1, we can't say that it exists because it's going two different places on two different sides. So we would say that this does not exist. Okay. So because that does not exist, but if they were both going to positive infinity, again, the limit technically doesn't exist, but we can say that as we get closer and closer to 1 on both sides, we are approaching positive infinity. Okay, so we have our vertical asymptote. So we have a vertical asymptote for f of x equals negative 2 over x minus 1 at x equals 1. So if we wanted to sketch the graph, we could do that. So we have a graph, we have a vertical asymptote here at x equals 1. That's the point at which it doesn't exist. As we're approaching 1 from below, we are heading to positive infinity. So we are going up like that. And as we are heading to 1 from above, we are approaching negative infinity. So it's going to look like that. And we have a horizontal asymptote at 0, which we could calculate by taking the limits to positive and negative infinity. Okay. And we will talk more about vertical asymptotes as we get into curve sketching.